In this presentation, we'll be discussing my research on the synthesis of novel isothioronium acylals as potential antifungals. Before getting into this project, it is necessary to provide a bit of background on the problems it attempts to address, namely antifungal infections. Despite the annual 1.5 million deaths globally associated with fungal infections, this issue is often overlooked compared to bacterial and viral infections. However, with the increased usage of broad-spectrum antibiotics, central venous catheters, and prosthetic devices, along with other factors such as increasing population densities in hospitals, particularly of immune-suppressed patients, the public health burden of fungal infections has greatly increased. To address this problem, we currently have three classes of antifungals: the azoles, polines, and echinocandins. One of the most important antifungals is amphotericin B, a polyne synthesized in 1955, which became the first broad-spectrum antifungal agent despite its numerous and severe side effects. Unfortunately, with our limited repertoire of antifungals, resistance is posing a great challenge as demonstrated by recent outbreaks of drug-resistant Candida auris, which we can see on the slide, across the country. In order to understand why this research focused on isothioronium acylals, it is first necessary to understand what these terms refer to. Isothiouronium is a functional group in the acid salt of thiourea. Research has continually shown this group's strong antibacterial and anti-cancer properties, properties caused by the induction of apoptosis or programmed cell death. Though this research focuses on fungal cells as compared to bacterial or cancer cells, apoptosis is a somewhat uniform process in that it is fundamentally the same in any cell. As such, that research provides evidence that this functional group may have antifungal properties. Here we can see the structure of the isothioronium functional group. Acylals, on the other hand, are an acid derived from two aldehydes or ketones joined by a central oxygen. Though this group has not shown antifungal properties or similar biological activity, its stability establishes it as one of the most useful protecting groups for carbonyl compounds, a trait that is especially important considering our use of 4-chlorocarbonyl phenylboronic acid, or CPBA, as a reagent. And here we can see the structure of the acyl functional group. This provided methodology is a general list of steps that the experiments, for the most part, followed. However, in cases where there is deviation, I will discuss that. The first step in these experiments is to clamp an oven-dried 50 milliliter round-bottom flask in an ice bath on a magnetic stir. Though this step says to use an ice bath, we opted to conduct the experiments at room temperature and as such did not use an ice bath. Next, a stir bar and 20 milliliters of cyclohexane, our solvent, was added to the flask. Once this is assembled, a drying tube must be attached and stirring should be initiated. At this point, measure out and add 0.00055 moles of zinc carbonate, 0.002 moles of volaraldehyde, and 0.002 moles of an acid chloride. Rather than being a reagent, the zinc carbonate is a catalyst. This type of compound decreases the amount of time needed for a reaction by lowering the activation energy. Next, stir for 1 hour and following this, add 0.002 moles of thiourea and reflux for 2 hours. By allowing evaporated product to condense and therefore not escape the system, refluxing allows us to heat up and stir the reaction mixture without losing any product to evaporation. Once this is done, gravity filter the mixture through a bed of solid sodium bicarbonate into a clean, dry 100 milliliter round bottom flask. Because many of the products ended up being solids, it was not always necessary to gravity filter the mixture or do the next step of rotovapping to remove the solvent. Rotovapping, or rotary evaporation, allows us to gently evaporate our solvent, effectively separating it from the rest of the product. Once these steps are completed, one should end up with an isolated product that can then have its mass and volume measured to determine the density and percent yield. Finally, once that has been measured, IR or infrared and NMR or nuclear magnetic resonance spectroscopy can be conducted, with the results being compared to those of the starting materials. Here we can see the reaction equation using CPBA. And here we can see the table of results of our 9 experiments. We can see that of the experiments conducted, only 2 were successful. Looking closely, we can also see that a specific few diagnostic NMR peaks were used to evaluate the success of an experiment, a factor that we will get into with our discussion and analysis of results. Despite our eventual deviance from this, the initial focus of this research was on CPBA. As such, a fair deal of time was spent attempting to find the most effective NMR solvent at producing good peaks, both for CPBA and all products created using it. This was discovered to be acetonitrile. Once the first 2 products were made, NMR analysis showed a peak around 9.5 diagnostic of the aldehyde group, showing that the CPBA and valeraldehyde did not bond, signifying failure of these experiments. In the third experiment, CPBA was substituted with p-thiochloride. The thiourea was left out. Based on the success of this reaction, it was determined that the CPBA, not the procedures themselves, were to blame for the experiment failures. Additional acid chlorides were then used to help understand why CPBA would not react with the valeraldehyde. NMR on these products showed that the valeraldehyde would react with these acid chlorides, but unfortunately the NMR triple peak diagnostic of thiourea was not present, meaning the overall reaction failed. However, there was one potential exception to this rule. As we will see on the next slide, product number 5, synthesized using methoxyacyl chloride, may have had this triple peak and as such was potentially successful. Because of this, product number 5 was set to be tested on fungal cells, in addition to product number 3, which would be used as a control due to the lack of thiourea. This image shows part of our reaction equation for product number 5, specifically the methoxyacyl chloride and the valeraldehyde. In order to illustrate how NMR was used to show the success or failure of these experiments, I will first explain NMR and then highlight the main peaks used for this analysis. Now, before we get into that, like I said, I'll explain what exactly NMR is. Basically, this spectroscopy highlights the hydrogen surrounding certain carbons. Now, this means 2 things. First of all, NMR can exclusively be used on organic compounds, hence why thiourea is not being shown in this analysis. Additionally, these peaks, by showing these hydrogens, shows the functional groups present, and therefore allows us to determine the success or failure of the reactions as I mentioned earlier. Here we can see the peaks diagnostic of the methoxyacetyl chloride. It is assumed that this peak will be present in the product as it is the main reagent. This circle shows the aldehyde peak located between 9 and 10. The disappearance of this peak in the product means that the bonding between the acid chloride and valeraldehyde was successful. As I said, this is the NMR of methoxyacetyl chloride and the NMR of valeraldehyde. This image is the NMR of product 5 itself. Here we can see the presence of the methoxyacetyl peaks. Notice the absence of a peak around 9.5 showing that the bonding between the methoxyacetyl chloride and valeraldehyde was successful. So far, the experiment seems successful. However, here is where the possibly successful comes from. As you can see, there is what seems to be a very small triple peak around 6.5. If that peak does exist and it is not just white noise, then it is indicative of the presence of thiourea, meaning the reaction was successful and the product is valid. Unfortunately, due to the COVID-19 pandemic, this research had to be paused, and as a result, no biological testing was completed. Because of this research should be used as a guideline for future research by showing what worked, what didn't work, and providing useful information such as the best NMR solvent for CPBA. Specifically, future work should focus on addressing the two main points of failure for this project. This includes the failure of the CPBA to bond with the valeraldehyde and the absence of thiourea in products using other acid chlorides. As I stated earlier, this research initially focused on CPBA, but as it was realized that these reactions were not working, the focus shifted to novel isothioronium acylals in general. This initial focus, and why researchers should focus on getting boronic acid and the valeraldehyde to bond, can be explained by the potent biological activity, stability, and safety in the human body. Compounds using boronic acids have repeatedly shown themselves to have potent antibacterial, anti-cancer, and even antifungal properties. Here we can see the structure of the boronic acid used in this research, CPBA. Although biological testing could not be conducted, I hope this research proves valuable to future researchers pursuing the discovery of novel antifungals. Finally, I would like to acknowledge the role played by Dr. Desmond H. Murray, Dr. Denise Smith, the Andrews University Department of Chemistry and Biochemistry, and the Andrews University Department of Biology in making this research possible.